The focus of this chapter is on solutions. So, question: if you are really thirsty, can you drink seawater? Will that help? Answer is no. Uh, it's too concentrated, and our kidneys aren't as good as filtering out salt, so this would actually dehydrate us. But seawater is a solution. It's homogeneous mixture. Solutions are homogeneous mixtures, and seawater depends on where it's at. On average, is about 3.5% salt. On our body, is about 0.9% salt. So this would not work, and this would actually draw water out of our body. And if we were thirsty, it would make us thirstier. So here shows seawater, and the solvent, what is most of there is water. And the solute is, well, sodium and chlorine, but there's other salts in there as well. So it's not just sodium chloride. Sodium chloride is the largest concentration of any of the salt that's in sea salt, but there's other salts as well. And as I mentioned before, the majority of this solution is called the solvent, or the component that makes up the majority of the solution. And then everything else is the solute. So the solvent dissolves the solute. And these solutions form because of the intermolecular forces, so the interaction between the solvent and solute particles. And seawater, as mentioned before, it's not a good thing to drink. Not surprising. And homogeneous mixture, it's two or more substances, and it varies. So, like with a salt solution, it's 0.9% in our body, and it's 3.5 or some other concentration in seawater. And I mean some other concentration. Places like the San Francisco Bay, for instance, has a little bit less, lower salt concentration. And it seems uniform, but it could have many things. And many things that are mixtures are solutions. So air is a solution. So it's a gas solution. Metal alloys, so like 14 karat gold, that's a solution as well. So, and generally speaking, things go towards spontaneous mixture. And uniform mixing tends to be more energetically favorable because it's by probability, at least. And mixing is spontaneous. So if you have pure water and you have some salt water, if you remove the barrier, the concentration tends to go towards a uniform concentration. And what drives this is actually something called entropy. So I mentioned before with seawater that actually drinking seawater will dehydrate you. So common solutions, gas solutions. So air is a gas solution. Liquid solutions, so you have gas dissolved in liquid. So club soda is carbon dioxide dissolved in liquid. That's one. You can get two liquid solutions. So alcoholic beverages are liquid solutions. Solid dissolved in liquid. So a solid salt dissolved in water. That's a solution. And solid solutions like alloys, those are solid solutions. And for aqueous solutions, water is a solvent, so, hence the word aqueous or aqueous. Sometimes depends on your accent, I suppose. Solubility, when something dissolves into something, it's said to be soluble. So sodium chloride salt is very soluble in water. And bromine, for instance, the gas slash liquid, it's soluble in methylene chloride. So also soluble in carbon tetrachloride as well. So you can have something that's soluble in many different things. And when something does not dissolve in something else, it's said to be insoluble. So oil is insoluble in water, for instance. And solubility of substance depends on its tendencies towards mixing and the type of intermolecular forces between the solvent and the solute, and the solvent in itself and the solute in itself. So why do things mix? Generally speaking, entropy. Entropy is disorder. So if I were to take a jar of candy, something like M&Ms, if I were to separate them out all into individual colors and put them into a jar, and then what would happen if I shake the jar? Are they going to mix, or are they going to stay all in their perfectly ordered layers? And the answer is they're going to mix. Well, probably, most probably. What's the chance of me taking a bag of M&Ms and all mixed up and throw them together, and then I shake the jar, and then they line up perfectly, amazingly in an ordered row. Is that possible? The answer is yes, that is possible. But it's very improbable. So it's improbable, and that's just with a bag of 200 M&Ms. Imagine if I have a large amount of something, say something like, I don't know, 6.02 times 10 to the 23rd of something. What's the probability of that spontaneously organizing into pure substances? And the answer is very, very, very low, much lower than my M&M trick. And so that's what's driving the universe. It's probability, simple probability. And that was a big deal for some people when they were learning about what's driving the universe. They're looking for some elegant, proper solution. And it turns out one of the major driving forces in the universe is simple math probability. And that driving force is entropy. And entropy is the measure of dispersal, sometimes also referred to as disorder. And it's things move towards a spontaneous drive of disorder, of craziness. And also gases will expand effortlessly into a vacuum. It'll just fill up whatever it can. So which statement is true? The true statement is ideal gases mix because it increases their entropy. Intermolecular forces, we covered this in previous chapter, and this is weak to strong. Dispersion are the weakest, then dipole, then hydrogen bonds, then ion dipole are the different types of forces. And when a solution forms, there are a couple different types of interactions. There's interactions between the solvent in itself, the solute in itself, and then the solvent and solute interactions. So if the solvent and solute interactions are greater than the interactions with themselves, the solution will form. If they're about the same, the solution will form. If the solvent and solute interactions are lower than energetically the attractiveness between themselves, the solution may or may not form. Depends on the difference, also the temperature. So increasing temperature increases the probability of the higher entropy states to form. So for solvent and solute to mix, they have to overcome all of the attractive forces that they have for each other. And to overcome these, this is endothermic. It takes energy. So it very much helps if the solvent and solute have a higher attraction. And the most you can fit into something, it's a quantity, and it's called solubility. It's how much you can fit in. And so some things, gases, they're always soluble with each other. There's two weak of interactions. Two liquids that are mutually soluble are said to be miscible. So in any amount, so alcohol and water are miscible. But oil and water, they're immiscible. They're not soluble. And the solubility varies with temperature and pressure. So a general rule, though, is like dissolve like, meaning that if it's polar, will dissolve polar, and nonpolar will dissolve polar, but also, generally speaking, nonpolar and polar will not mix. And some ionic compounds will dissolve in polar solvents. So if the solvent-solute interactions in the mixture are comparable in strength, and the solvent-solvent interaction in the solution, what can you conclude about this? This solution is going to form. But also, it's going to be entropy-driven. Consider a table listing the solubility of several alcohols, water, and hexane. Which statement can you best describe the overall observed trend in these intermolecular forces? So looking at these, as the carbon chain gets bigger, the solubility in water goes down, and the solubility in hexane goes up. So just looking at this chart, that's a general trend, and there you go. So heat a solution, this is the amount of energy it's released when things dissolve. So sodium hydroxide, for instance, when you dissolve this in water, it gets really hot. It really does get really hot. I have to be careful whenever I make sodium hydroxide solutions in the lab. When you get ammonium nitrate dissolved, it gets cold. So this is used frequently for icy cold packs. So why is this? Well, if the solution, to separate the solution into its contiguous particles, it's endothermic. So, and the same thing with the solvent and the solute. But then mixing the solvent and the solute particles, this is exothermic. So the overall solution, the overall heat of solution, is the combination of these three components. And so separating the solvents is endothermic. Is that the solute? Solute. I'm sorry, that's the solute and the solvent. These are both endothermic. Now that mixing these together, it's exothermic, and it depends on the relative strength of them. If the overall process is, or if the mixing process is greater than the other two steps, the overall process will be exothermic. If it's less than, it's going to be endothermic. Endothermic going to be absorb energy. And the heats of hydration, generally speaking, the attractive forces between the ions, this is the lattice energy. So the heat of breaking the solute apart is equal to the lattice energy, or the opposite of how much energy it takes to rip apart the lattice. The attractive forces are then the ion dipole, at least in water. So the hydration is the mixture of the heat of solvation and the heat of, the heat of breaking apart the solvent and the heat of the mixture. So the heat of hydration here, this shows so potassium fluoride. The first step is the lattice energy, at least the opposite of that lattice energy, and then the hydration then is the exothermic step. But the overall solution formation is going to be endothermic by +2 kilojoules per mole. So when ions dissolve in water, they become hydrated, and they're surrounded by the water molecules. And this is opposite charge is attracted to each other, so this is going to be an exothermic process. So the heats of solution for ionic compounds, it's going to be, you can see the first start, this is what we said before, the solute and the solvent, and the heat of mixing. The solute heat is minus the lattice energy, and then the heat of solution then is going to be the hydration minus the lattice energy, or minus the lattice energy plus the heat of hydration, however you want to organize it. That's organizing it the same way. So because lattice energy is exothermic, the heat of solution tells us something about the heat of hydration. If the heat of solution is large and exothermic, then the amount of energy it costs to separate these ions is less than the energy released from the hydrated ions. If the heat of solution is large and endothermic, then the amount of energy it costs to separate the ions is much more than depends on the variance. It's more than the energy it gets than the energy is released from hydrating the ions. If it's about the same, then the heat of solution is 0. In the solution equilibrium, dissolving particles is an equilibrium process. So meaning that it's also dynamic equilibrium, meaning that some are dissolving and some are precipitating back down. So when there's no dissolved solute, the process is only in one direction. But after it starts going that direction, then there's the reverse reaction is also happening, or reverse direction. Eventually, you get to a point where the rate of deposition and the rate of dissolving equals each other, and then no more of the solute will dissolve. And when you get to this point, we call this a saturated solution. So you have salt, and over time, you get to a point where the solution reaches an equilibrium where no more will dissolve. And that's if you have to keep on adding salt, though. If it's soluble, if it's below the soluble amount, it'll all mix in together. So a solution that will not hold anymore, this is known as saturated. And I can tell you, making saturated sodium chloride solutions, it takes a lot of sodium chloride to make a saturated solution. It's surprising how much you can do that. And a solution that has less solute is said to be unsaturated, so more will dissolve. And a solution that has more solute than saturation is said to be supersaturated. And I can tell you something that's kind of fun is to make a supersaturated sugar solution. So you can take sugar and water, and you can heat up the solution, and more will dissolve. Then you cool the solution down, and it becomes super saturated if you add enough sugar. And then you can crystallize the sugar out, and you can make rock candy. So that's a fun little experiment you can do at home. So how can you make a solvent hold more solutes? So there's some things. So I already mentioned heating the solution, also they can be unstable under certain pressures. So for instance, a carbonated beverage, if you shake it up, you can get it unstable. You can lose the solute above the saturation point. So, and you can crystallize things. So this is sodium acetate to a supersaturated solution. A little adding of a crystal can then give it a surface to grow on. You can quickly grow a bunch of sodium acetate crystals. And temperature dependence, generally speaking, increasing temperature increases solubility. And the reason for that, we'll learn later, there's something called Gibbs free energy. Delta G equals delta H minus T delta S. So, and negative delta G is spontaneous, so that minus T delta S, increasing the temperature, increases also the entropy forces, and so then those become more favorable over higher temperatures. So, and generally speaking, though, because of entropy, things in general will dissolve more. There are certain circumstances well, it's very rare, but there are some circumstances where temperature will decrease solubility. Gases, it's always the other way. I said gases are increases temperature, they decrease solubility. So here's the temperature dependence on solubility. So solubility on the y-axis, temperature on the x-axis, and you can see the very most common general trend is increase. And you can crystallize things. So one of the purifications methods is to crystallize things. And you saturate a solution, and you cool it down. As the solution cools, the stuff precipitates out of the solution. And I already mentioned that with doing it with sugar. You can do that to make rock candy. But you can do this for other things. Certain drugs are made this way. It's easy to make aspirin, for instance, this way. Acetylsalicylic acid, also known as aspirin, can crystallize it out by cooling a solution. And gases and water, generally speaking, they have lower solubility, and the highest solubility are the ones that react with water. So ammonia and carbon dioxide, for instance, react with water. And for all gases, solubility of gas decreases as the temperature increase. So because of entropy, entropy favors having gases in the gas phase, not and less ordered in the liquid phase. And so you can see this with warm soda on the right versus cold soda on the left, that the warm soda is going to fizz more. So solution is saturated with both nitrogen gas and potassium bromide at 75 degrees Celsius. What's going to happen if the solution is cooled? What's the most likely thing to happen? It's the potassium bromide is going to precipitate out. And temperature dependence of solubility of gases and water. Pressure dependence. Pressure dependence. Generally speaking, the higher the pressure, the more solubility. And many sodas, for instance, you pressurize them under higher pressures, and then when they are exposed to atmospheric pressure, they become bubbly. And a way to observe this is using Henry's law. Henry's law is the solubility of the gas equals the Henry's law constant times the pressure of the gas. And that kH, that's the Henry's law constant, and there are some of the Henry's law constants for the different gases in the units of molar per atmosphere. So concentrations, we've already mentioned concentrations in moles per liter, but concentration is just a way of saying how much stuff there is. So dilute and concentrated to say relative amounts of how much something is in. And we use different terms for concentration. Some of the units, you're already familiar with moles per liter. There's molality. Molality is moles per kilogram solvent. Mole fraction is just the number of moles of whatever and over the total number of moles. It can be the solute. It can also be the solvent as well. Mole percent is just the mole fraction times 100%. Parts by mass, it's just the mass of whatever you're looking at over the mass of the total mass times some multiplication factor. So if it's percent mass, it's 100. That's multiplying factor. Parts per million is 1,000,000. Parts per billion is 1,000,000,000. And the last part is parts by volume. It's just the volume of whatever it is you're looking at over the total volume of solution times the multiplication factor for for percent, it's just 100. There's other types. Frequently in alcohol beverages, you use the proof, and the proof is just double the concentration. So, for instance, 40% ethanol, 60% water solution is known as 80 proof. It's just twice the 40%. Preparing a solution, there are some things you need to know. You need to calculate the mass of solute needed, and then start with the amount of solution, and then you can mix them. You can also use concentration as a conversion factor. So 5% by mass, you have 5 grams of solute, and then 100 grams of solution. So it's easy using water because water's density is 1 gram per milliliter. Then you would need 95 milliliters. But for a different solvent, you have to be careful of the density. And then you dissolve it to have the total amount of solution. So for instance, making 1 molar sodium chloride, making 1 molar sodium chloride, you add a mole of sodium chloride, and then you add amounts of liquid till you get to a liter, and it dissolves. So a solution concentration, molarity, it's moles per 1 liter of solution, and you should be very familiar with this, hopefully at this point in time. As we've talked about, we've used molar quite a bit in this class up to this point in time. If it's your first chapter coming in, molar is moles per liter. And molality is different. This is moles solvent per 1 kilogram, moles solute per 1 kilogram of solvent. And it's kind of like molar, but not, there's different numbers. So be careful. They're not the same thing as molarity. So molality, also known as small m, that way. So if you combine 25 grams of solute that has a mass of 25 grams per mole with 100 grams of solvent, what is the molality? Well, that's 1 mole over 0.1 kilograms. That means 10 molal. And the m is molality, so that's 10 molal. Parts and solute in part solution, you do mass or volume. Parts are usually measured in the same units, for instance. So by mass in grams, kilograms, pounds, and so on. For volume, milliliters, liters, gallons, and so on. And mass and volume, you can combine in grams and milliliters. So percentage, it's per 100 parts of solution. If it's 0.9%, that means there's 0.9 grams per every 100 grams. Parts per million, for instance, 36 parts per million by volume, there is 36 milliliters over 1,000,000 milliliters of solution. So ppm, parts per million, grams of solute per 1,000,000 grams of solution, or a milligram of solute per 1 kilogram of solution. So a liter of water is a kilogram. So you can use this as a conversion factor. Parts per billion, same thing as million, but instead of a million, it's a billion. So 10, instead of 10 to the 6 is 10 to the 9. Mole fraction, this is the amount of moles of one substance divided by the total moles. If you sum up all the mole fraction, it equals 1. And there's no units in this because the moles cancel. Moles over moles, the moles cancel. The mole percent is the mole fraction times 100%. So converting concentration units, write the concentrations as a ratio, separate the numerator and the denominator, separate the solute and the solution part, convert the solute to the required unit, convert the solution to the required unit, and use the definitions to calculate new concentration units. So that's like if you want to convert between molar and molal, for instance. But you would need to have certain information. And the terms of for molal, and between molal and molar, you would have to know the density, for instance. So colligative properties. Colligative properties are properties that depend on the number of particles. So the number of particles, not and this affects the concentration of the particles in solution. So what I mean by the number, if you dissolve sugar, sugar is a molecule, that's one particle. You dissolve sodium chloride salt, that breaks apart into 2 particles. So the fact that there is twice as many particles in sodium chloride salt is going to affect the colligative properties differently. And the colligative properties we'll learn soon, like freezing point depression, vapor, boiling point elevation, vapor pressure, and osmotic pressure. These are colligative properties. So the vapor pressure, the solutions, the vapor pressure of the solvents is lower. So the solution, having a solution, lowers the vapor pressure of the pure solvents, and it does so by the attractiveness. So it overall decreases the amount of vapor above the solution. Eventually, after adding a solvent, the equilibrium is reestablished. So this is saying the equilibrium is going to be reestablished. And the thirsty solutions, so thirsty solutions are if you have 2 solutions together. So here, if you have a pure solvent and a concentrated solution, actually over time, if it's a closed system, so this only works in a closed system, the pure solvent will work its way over towards the solution. And eventually there would be a equilibrium, and then the solution will not change as much anymore. So the change here, this is known as Raoult. Well, the way that the vapor pressure changes is known by Raoult's law. Raoult's law says the vapor pressure of the solvent in solution is the mole fraction of the solvent times the normal vapor pressure, that temperature that the solvent would normally be. So conceptual connection here. What is a vapor pressure solution in which the mole fraction is 0.2 and the vapor pressure is 100 torr? So it's just 0.2 times 100 torr, or 20 torr. So vapor pressure lowers. The vapor pressure lowers. The solution is always lower vapor pressure than the pure solvent, and this is also a colligative property. So when you look at the mole fraction of the solution, well, how much it changes, it's the mole fraction, but it's also in particles. So remember that when you do the calculation. So sodium chloride, for instance, is going to be, even if you put 1 mole of sodium chloride, it's actually 2 moles of particles. So 1 mole sodium, 1 mole chlorine. And Raoult's law here for volatile solutions, if you have a mixture of things that can both evaporate, then you have just the total pressure is just the vapor pressure of the solvent and the solute. And then the mixture, though, it follows through them with really just a straight line. Looking at the graphs. I'll show you the graphs soon. And for non-ideal conditions, it depends on the types of interactions. So if the interactions are stronger than or if they're weaker, this is going to have non-ideal behavior. So, and the non-ideal behavior depends on the circumstance. If the solvent, solute, and the solvent well, if the solute-solvent interaction is stronger than the individual component, then the vapor pressure will be less. If they're weaker, then the vapor pressure is going to be higher. So this graph here, so looking at the y-axis is the vapor pressure, and on the x-axis is component X, mole fraction of component A. So on the left, when your mole fraction of A is 0, that means you have all of the second component, B. And so if we start with the ideal, looking at it is just the straight line between the two. You have the vapor pressure of pure A on the right and vapor pressure pure B on the left, and it's a straight line. If there's stronger interactions, there's going to be a deviation. It's going to be lower than. If they are less than the interaction, you're going to have the vapor pressure is going to seem to be higher than it would normally be. Then it would be a deviation from the ideal, is what I mean. So other colligative properties related to vapor pressure. So boiling points. So boiling point elevation, it goes up. And also freezing point depression. So freezing point goes down to this. And again, this is colligative property, means it relates on the number of moles of particles. So looking at this is the phase diagram for water. And in the pure water situation, you have that. If you have a solution, you increase the amount of how much the liquid phase exists. The existence of the liquid phase exists from there, and we it's one of the reasons why I use antifreeze, so that the water doesn't freeze in the pipes of your car. So freezing point depression. So the change in temperature is going to be the molal times the freezing point depression constant TF, or I'm sorry, KF. So M is molal and KF. The units on KF are degrees Celsius per molal. And remember, the molal here is the moles of particles. So here are some values of KF and KB at various temperatures. Various temperatures at various things. And you can see also the normal freezing point and the normal boiling point for these. Boiling point elevation. Boiling point of solution is higher than the boiling point of the pure solvent. So for a non-volatile solute, so this is different than a mixture. Right, so the mixture of two volatile for a volatile solution with the solvent and the solute being volatile themselves. So this is like salt or sugar and water, for instance. And same idea with the boiling with the melting point depression. This is the boiling point elevation. Similar process. So osmosis. Osmosis is a flow of solvent from a solution of low concentration to a solution of high concentration. So, and these solutions are separated by a semipermeable membrane. And the semipermeable membrane allows solvent but not solute to flow through it. And the osmotic pressure to keep the flow, to keep the flow from taking place. This is known as the osmotic pressure. In the osmotic pressure, we use the capital Greek capital Greek letter pi. So, and it's the same thing as the ideal gas law, PV equals nRT. But instead of pressure, we have pi, and then we take volume, and we have N over V, moles per volume, moles per liter. So it's really just the ideal gas law, but it's rearranged. Instead of pressure, we have pi, and instead of N over V, we have M for molarity. So here is the osmosis cell. So you have a solution on the left, and then the pure solvent on the right, and then you have a semi-permeable membrane. And what happens is the solution draws some of the solvent particles into there, and then there's a pressure. Then there's a height difference, and eventually this reaches an equilibrium, and you can measure the height difference in this. This is known as a U-tube apparatus, and you can see it's in the shape of a U. And and you can determine the pressure by the height of the water. So 10 meters of water, for instance, is equal to an atmosphere of water, 760 millimeters of water. Or, sorry, 760 milliliters of mercury. The Van Hoff factor, it's the, I mentioned that it's these colligative properties are based on the number of particles. The Van Hoff factor, though, is what we actually observe. So it's usually less than the theoretical pairing. And where does the Van Hoff factor comes into play? Well, if you look at the solution of sodium chloride, two of the, like a sodium cluster and a chloride cluster, they can kind of come together and they can pair together. And now this ion pairing behaves like one particle rather than two. And so because of that, instead of seeing two particles from sodium chloride, we see about 1.9. So that factor is known as the Van Hoff factor. So look at this. Which solution has the highest boiling point? You have half molar. They all half molar, but we have glucose, which is, that's sucrose. You have sucrose, which is one particle. You have sodium chloride, which is two particles. And you have magnesium chloride, that's three particles. Colligative properties, it's the one with three particles. And some of these medical applications, so an isomotic solution has the same osmotic pressure of a solution in the cell. So there's no wet net flow of water in or out of the cell. So this is very important for IVs, of course. So here's a normal red blood cell. If you have a hyperosmotic solution, so if you have too much salt, that means that the water will flow out of the red blood cells, and you'll get shriveled up red blood cells. On the other hand, if you put in pure water, so if you inject pure water into the body, now what happens is the water will rush into the red blood cells and make them large, and you can actually get to the point where you'll burst the cells. So that is an issue with injecting pure water into patients. So I've mentioned this. Mixtures. So solutions are homogeneous, and suspensions, these are heterogeneous. So you can see that they will separate on standing. So colloids are heterogeneous, but they do not separate on standing. So particles can coagulate, and they cannot pass through semi-permeable membranes. They're also hydrophobic, so stabilized by attraction for solvents. They can be hydrophilic, or they can be hydrophobic. So they can be stabilized by attraction to solvent, and they can be stabilized by surface repulsion. And you can see this in water. So things like you can see particles suspended in them. And the Tyndall effect. So it shows the Tyndall effect and Brownian motion. Tyndall effect is the scattering of light. So, here I'll show you pictures of scattered light in a second, but let's look at these different types of colloidal dispersions. An aerosol. This is a liquid dissolved in a gas, and so fog is an example of this aerosol suspension. Solid aerosol is a solid and a gas, and smoke is that type. Foam is gas dissolved in liquid, so whipped cream is when, if you ever made whipped cream by hand, it's hard it takes a lot of effort to whip all that cream. A liquid emulsion, you can get two immiscible liquids like fat, fat and water. So milk, for instance, is a liquid emulsion. And you can get a solid emulsion where you have a liquid dissolved in a solid. So opal, for instance, is water in a silica glass, for instance. Brownian motion, this is just the overall motion that occurs in is in atoms and liquid. And this was one of the first things observed improved for atoms. And with also a soap. Soap forms a colloid because of its unique structure. There's a hydrophilic end and a hydrophobic end. Most soap is anionic, where you have the and like the usually it's a fatty acid, so it's in the acetate end on it. So oil acetate, the carboxylic acid, the negatively charged end of the fat, and this allows to form a structure called a micelle. And here is soap. You have the nonpolar tail and then the ionic head. And so sodium stearate. This is just generally stearic acid. That's a fatty acid, also frequently found in animals. And you can mix soap to form the suspension. Forms a micelle. So, for instance, you have a droplet of dirt or oil that's not dissolved in water. So, meaning like, okay, say you're cooking with some food and you have olive oil on your hands, and you can take olive oil and you can rub your hands under water. Nothing happens. You can get some of it'll come off by friction, but you still have this oily sheen on your hands. But then you put soap on your hands and you mix it with water and you rub it together. And it's important that you rub your hands together with that, and then you clean all the oil off your hands. Why is this? How does magic process happen? Well, the oil is nonpolar and water is polar. They don't mix, but soap has a nonpolar end and a polar end. The nonpolar ends surround the oil droplet, and then the polar ends stick out, and that's known as, this whole structure is known as a micelle. And you have to rub your hands together to mechanically make the micelles. This is very similar to a cell membrane. A cell membrane is a phospholipid bilayer, so you have two layers in a cell membrane. Tyndall effect. The Tyndall effect is light scattering. So you can see sunbeams, for instance. When you see sunbeams, you're seeing the scattering of light from solid particles suspended in air, or also for fog too. If it's you could do that for fog. Like if it's a foggy night, I remember we used to take flashlights, go outside, and pretend like they're lightsabers, like the Star Wars things. So, or if it's smoky, you can do that too. Pretend like flashlights are like the lightsabers. You can see the beam of light. So that's the Tyndall effect. Is a scattering of light. And so if you look in this solution here. Well, actually, the one on the left, closer to the light source, is not a solution. That's a colloid, because you have the scattering of light. The one on the right is a solution, so it has no scattering. So it's a homogeneous mixture. The other one is a heterogeneous mixture. And micelles also, they form repulsion, so they don't go into big blobs because their surface is negatively charged. And you can make just the suspensions there, and you can make them wash away also. Well, in this case, you put them in a beaker in solution, and then they'll scatter light with a Tyndall effect. And we're done. Thank you for joining us.